Nice. All right. What we're going to talk about today is we're going to start on writing and balancing equations. And this is where we really, we've done plenty of stuff that's like chemistry stuff, but this is the section where we really start to get into stoichiometry. We really start to get into some things that, as we do them, are very much going to feel like some really good chemistry work. So, this is pretty interesting. It's not hard. Close your Chromebook. Are you still working on the quiz? Are you really? All right. Whenever you're done, close your Chromebook, though. Pretty sure I thought only one person was still working. So, let's see. With this kind of work, it's all about writing down what you're doing. Using scratch paper, taking little notes. If you try to just do all this in your head, some of you might be able to do it, especially for some easy problems, but once it gets harder, you're going to want to write this stuff down. And as you see me do it, I always write stuff down on the board. I'll always have a scratch piece of paper. And so, don't be lazy. Get your scratch paper out. Make sure that you're writing stuff down, and this will be fairly easy. What we're starting with today is the law of conservation of mass and balancing equations. And we're all somewhat familiar with the law of conservation of mass. What does the law of conservation of mass state? Yeah, mass cannot be created or destroyed. If I have an atom, it's going to be an atom. It's not going to go anywhere. I can't make new atoms. And I can't just make an atom disappear. Now, when you get into advanced physics, you get a little addendum to that, in that matter cannot be created or destroyed just out of nothing. But Einstein wrote one of the world's most famous equations, just because popularity. What's Einstein's equation? E equals mc squared. And so in this equation, Einstein theorized, and as the equation became proven, he also proved that while mass cannot be created or destroyed, it can be converted into energy. So small amounts of mass can be converted into energy. I just want everybody to be aware of that. It's like a little side part of the conservation of mass theory. But we're not going to get too deep into that. We're just talking about chemistry. And for these purposes, yes, matter cannot be created or destroyed, especially in a chemical equation. And so if I put an atom into a chemical equation, if I put it into the beaker, it's going to come out of the beaker. Even if it's in a completely different chemical, whatever goes in must come out. That's the law of conservation of mass. So we're going to start with a couple easy definitions. A chemical equation is an equation that shows the rearrangement of atoms that occurs during a chemical change. So chemical equations are used to show chemical reactions, all right? So if I'm doing a chemical reaction, I should be able to write it out in some sort of equation that kind of illustrates this for me or anyone else that I'm trying to show. In that equation, we have two things. We have reactants and products. And the names kind of help you, remember which is which. Reactants are the things that are going to react in my chemical equation. They're the things I put in first, and they react with each other, and they make something new. Now, when I make something new, that is called the product. So in a chemical equation or chemical reaction, let's say it happens in a beaker in lab, the reactants go in, the products come out. Products are what I produce. Reactants are what are reacting inside my beaker. So the reactants go in, the products come out. And that's going to be the same thing in my equation. If I write out an equation, the things that go in are going to be on the left, and the things that come out are going to be on the right. So reactants on the left, products on the right. And the arrow usually tells you that you're going one way. There's not a lot of chemical reactions. There's some, but not a lot of chemical reactions that can go back and forth. Most of them are only one way. You can't undo a chemical reaction, at least not in the way that you think. So here's just a generic example. Instead of using real chemicals, they just use letters. So they have A plus B is equal to AB. So I take the chemical A, add the chemical B, and whatever they combine creates a new product called AB. Now, they're going to talk about states of matter a little bit. We all know the basic states of matter: solid, liquid, gas. There is a little like important distinction, because we have two things right here: liquid and aqueous. Does anybody have a guess as what's the difference between liquid and aqueous solutions?
Aqueous solutions, solid.
No. What does aqueous sound like?
Water.
Water. Okay. And is everything that's liquid water?
No.
No. So what I have here is hydrochloric acid. What form is this in? Liquid. Is there any H2O in here? No. This is hydrochloric acid. It says on the label HCl. So there's no H2O. There's no water involved in this beaker at all. Now, if I take something like a solid, like let's say salt. I have like a solid salt, like just like the salt you sprinkle on your food or your French fries. What if I want to do a chemical reaction with that and I need it in liquid form? Salt would have to be really, really hot to melt all the way down into a pure liquid. But what can I do with salt?
Dissolve it.
I can dissolve it. I can dissolve it in water. Now, if I dissolve it in water, is salt the only thing left in that beaker? No, now I have water in there. And so basically, if you see this AQ, this is an indication to you that what you're dealing with is a liquid. So like salt dissolved in water would be a liquid, right? But it's also telling you that I have water that's in there that isn't part of my reaction. It's not part of my equation, but I need to know that it's like dissolved into water. And so that's the difference between a liquid and a aqueous solution. A liquid is a pure version of whatever chemical you have there. So like this one is water and it's liquid. Obviously, that's just pure water. They don't have another liquid over here. But let's say I had like CO2 dissolved into a glass of water, like carbonated water. That's going to be an aqueous solution because it's dissolved in water. There's water there. It's not part of my formula. It's just something that's like carrying my chemical in a way. So everybody just be aware of that. We're not going to use these too much, but you will start to see them included in your problem. So that's what they're telling you. Is it a solid, a liquid, a gas, or is it dissolved in water or in some other form of water? So now let's introduce coefficients and subscripts. We already used subscripts quite a bit. I want to make sure everybody knows what's up with the coefficients. So if I have, let's say just H2O, this is a subscript. And this too only counts for which element, the hydrogen or the oxygen? Hydrogen. So if I have H2O, I have two hydrogens and one oxygen. Everybody's comfortable with that, right? Now, what you're going to start to see in these problems, which I don't think we've seen too much of before, they're going to start to put big numbers up front. And this big number is called a coefficient. The little one is called a subscript. So like script is writing, sub means lower. So it's the little script, the little writing underneath everything else. This one's called a coefficient. C-O-E-F-F-I-C-E-N-T, I believe. Maybe that's right. So this is your coefficient, and this is going to multiply for everything. So if I have a 2 in front of here, now I have 4 hydrogens and 2 oxygens. Is everybody comfortable with that? Mm-hmm. The reason why we use this, though, is, so if I have 4 hydrogens and 2 oxygens, couldn't I just rewrite the formula to be H4O2? Yes, but now here's the problem. Is that water? No, that molecule is not water. It has the same number of atoms as the stuff up here, but it's a different formula. And so the reason we use a coefficient is to show you I have twice as much of this type of atom, but I'm not changing the atom. This is still a water molecule with 2 hydrogens and 1 oxygen, but I have 2 of those water molecules. Does that make sense? If I double everything in the formula and still write it as the formula, this is no longer water. technically. If I made this molecule, it wouldn't be a water molecule. So the coefficients don't change like your overall molecule. It just tells you how many of those molecules you have. Is everybody comfortable with that? So the coefficients are going to multiply by everything behind them when we have those. Now, let's see what they get to next. We already talked about the law of conservation of mass, and they're basically going to tell you the total mass, the weight of all the stuff that goes into your beaker needs to equal the weight of all the stuff that comes out. So whatever goes in has to come out. It's not just by the weight, it's the number of each type of atoms. If I put 5 oxygen atoms into my beaker, it doesn't matter what other chemicals are in there, what chemical reaction happens, 5 oxygen atoms have to come out. There's no way around that. Whatever goes in has to come out. If it doesn't go in, it can't come out the end. It's got to be equal on both sides. And that's what we're dealing with here. We're going to be balancing equations. So that's what they introduce now. A balanced equation is one where all of your coefficients and all of your subscripts add up on both sides. Everything that goes in comes out of your beaker, and everything is nice and balanced. If your equation is not balanced, we call it a skeleton equation. Usually your skeleton equations are going to be missing these, the coefficients. If I see an equation that has coefficients, I'm going to double check just in case, but I can assume that equation is balanced because there's no other reason for these to be here other than somebody balanced them. If I see an equation and it doesn't have any coefficients, I'm going to assume that it's not balanced. Maybe it is after I check, but I got to assume that it's not. It is probably a skeleton equation. So this is just an example of a balanced equation. How many nitrogens do I have here? 2 nitrogen atoms. How many hydrogen atoms do I have here? 6. And they're paired up as N2 and H2. Then I form ammonia. And notice, even though the chemical is different and it's a different formation, it's the same number of atoms. I have 2 nitrogens and 6 hydrogens in this new chemical that I've created. So everything that goes in has to come out the other side. There's no way around that. So what we do to balance these equations is our job is to add the coefficients. And we need to add coefficients to each chemical until it's balanced. It sounds really easy, but once you get started on this, you'll see how it gets a little bit confusing. You need to write stuff down and keep track of it. So we'll get a couple examples here in a second. So to balance an equation, it requires trial and error. And this is true. You're not going to be able to get it right the first time. You're going to have to write stuff down, scratch numbers out, recount things, see if that works, try something else. This is a trial and error kind of assignment here. So it is helpful to balance the equations in this order. You want to start with your metals and your complex ions that have multiple atoms in them. Move on to your nonmetals. And the most important thing is save the oxygen and the hydrogen for the end. And the reason is most of your chemicals have oxygen and hydrogen. If you try to balance these first, by the time you go back and balance the rest of the stuff, your oxygens and hydrogens will be off again. And so because they're the most common thing to be in an equation, you want to save these till the end and do them the very last. And that will help you out, especially if the oxygen or the hydrogen is by itself. It's like O2. Save the O2 till the end. Do it at the very last. Start with everything else. That's really important. So step 1, you need the skeleton equation. Write it down, or Sapling will give it to you, but you should probably write it down because you're going to be using scratch paper. Step 2, count and write down the number of atoms of each element on the reaction and product side of the skeleton equation. Step 3, balance them using coefficients. Add in your coefficients, multiply everything out, and redo your count. So we're going to do an example here. Step 4, double check everything. Make sure that you can't reduce. We've already talked about reducing a little bit. So see if you can reduce your coefficients. So here's your example. Write the balanced equation for the chemical reaction describing the following statement. When dihydrogen monosulfide gas is bubbled through an aqueous solution of silver nitrate, it produces nitric acid and solid silver sulfide. So this is written out. They normally don't write this out where you have to get all the chemicals, but let's do this as it's written, and we can kind of get going on this. So, what's the first chemical they tell me I have there?
Hydrogen.
It's what?
Hydrogen.
Does it say hydrogen, or what's it say?
Or dihydrogen.
Dihydrogen, which means what?
Two.
Two hydrogens. So I have H2 what?
Monosulfide.
Monosulfide. So this first one, dihydrogen monosulfide, is H2S. And what am I adding to the H2S?
Nitrate.
It's bubbled through an aqueous solution of silver nitrate. So silver is what element on the periodic table? Ag. Au is gold.
Yeah.
So silver nitrate. What is nitrate? Does anybody have a guess at nitrate?
Nitrogen.
Na. Wait, no.
It is nitrogen, and what else would be in nitrate? Oxygen. Nitrogen and oxygen. So it's probably NO3. To be fair, what is NO3? We might have another silver here. I'll have to look at the formula in a second. So we have our silver nitrate. We're not 100% sure that's the complete formula, but we'll check it out in a second. And then what does it turn into?
Nitric acid.
It produces nitric acid and solid silver sulfide. So we're going to have the silver with a sulfur, and we're going to have nitric acid, which is going to have hydrogen and NO3. So we're going to have something like this. I guess it would be AGS. AGS plus HNO3. I don't know how many hydrogens that goes to. Let's see if we got these close to right. So basically, you want to do these right. You're going to look them up on the periodic table, figure out the charges on these. So like hydrogen would be a +1. Sulfur would be a -2 because it's over there with oxygen, right? Yeah. Sulfur would be a -2. Nitrate, I'm guessing, would be a -2, and your silver would be a +2. Let's see if I'm right about that. No. Your silver is going to end up being a +1, and your nitrate's a -1. So I got the HNO3 correct. I need an Ag2 here. Ag2S. So that's right?
Mm-hmm.
HNO3, Ag2S, AgNO3, and H2S. So we have our setup now. What you need to do every time you get one of these problems, first off, like I said, they're not going to give you the word problems too often. Most of the time, this is what they're going to give you straight from the beginning, and they're going to tell you to balance it. What I need to do to balance it is I need to make a T-chart. This is really important to do this and make sure that you're doing it correctly on both sides. So what I need to do is get my chemicals in here and start to count them. So what are the chemicals that I have? I have hydrogen, I have sulfur, I have silver, Ag, I have nitrogen, N, and I have oxygen, O. Is that all the chemicals? Yes.
Yeah.
Now I need to count them on the left side and the right side. This arrow here is your reaction happening. So everything to the left of the arrow is called what?
Reactants.
Reactants. Reactants are what goes in. Products are on the right side. They're what comes out. And so I'm literally just going to count how many atoms do I have in the reactants, how many atoms do I have in the products. So here, how many hydrogens do I have?
2.
2 hydrogens. How many sulfurs? 1 sulfur. And actually, instead of Roman numerals, let me use the actual numbers. So I have 2 hydrogens, 1 sulfur, 1 silver, 1 nitrogen, and 3 oxygens. Over here, I have 2 silvers, 1 sulfur, 1 hydrogen, 1 nitrogen, and 3 oxygens. Okay, so now what is off between the left and the right side? What's different?
The
Hydrogen and silver. Which one should I balance first?
Silver.
Silver. And why is that? What should I save to the end? Hydrogen and oxygen. Save your hydrogens and oxygens to the end because they're more common. It'll be easy to balance if you do them last. So I'm going to start with the silver. Which side do I need more silver on?
The left side.
The left side. But watch what happens when I do this. So how you balance equations is you add the coefficients. You add a coefficient in front, and you get the number that you need. So how many silvers do I need over here?
One more.
Well, I need one more, but I need a total of 2. So what I'm going to do is I'm going to double this, and that gives me 2 silvers, right? But it doubles everything on this side. So I need to redo my count. My 1 silver turns into 2. My 1 nitrogen turns into 2. And now how many oxygens do I have? 6. So notice I changed my silver, and what happened? My oxygens changed. This is why they tell you to save your hydrogens and oxygens to the end, because they're probably going to change. Now, I'm good on this side. What do I need on the other side? I need more oxygens, I need more nitrogens, and I need more hydrogens. If I put a 2 here, that just might fix everything. That gets me 2 hydrogens. That gets me 2 nitrogens and 6 oxygens. And so now, am I even?
Yes.
Yeah, I'm even everywhere. I've added a coefficient of a 2 here. I've added a coefficient of a 2 here. Now everything's balanced. And so basically for a sapling problem, they would have this equation already in the answer box. And what you have to do is go in and put that 2 there and that 2 there. And once you put those into the answer, you can hit check answer and it'll count it right. So let's see if they got another example. And then maybe I'll turn y'all loose on the assignment. So they did the same thing. We got our first counts. They added a coefficient of 2 on the left side, which changed their count. They added the other coefficient of 2 on the right side, and then everything's nice and simplified. Oh, last step. Can we reduce this at all? Our coefficients here, if there's nothing here, how many of these molecules do I have? Just 1. No, I didn't mean the hydrogen specifically, but like the whole thing here. Just 1 of those, right? If there's no coefficient, I have 1 of that molecule. So our molecules here are 1, 2 of those, 1 of these, 2 of those. Those are our coefficients. 1, 2, 1, 2. Can I reduce that at all? No. If I have a 1, I can't reduce anything because I can't have like a half of something. So these are good on your coefficients. Now, if I did all this and I balanced everything and I had coefficients of like 2, 4, 6, and 2, I can reduce that, right? They're basically making sure that you reduce everything. Because sometimes you go through this and it gets so confusing. So many things are changing. By the time you get to the end, your numbers are a little big. So you could go through and reduce these down to 1, 2, 3, and 1 by dividing by 2. And that will be your correct answer as opposed to the other one. So just keep an eye on that. You'll get that from time to time depending on how you go through the rest of the problem. And no, that was it. So go ahead and open up your Chromebooks. Give me just a second because it's not assigned right now. I don't know if we would get time to get to it. And then you can get started.